Welcome back again, dear students. The topic number is EMWG-S3 and the title is phase velocity and group velocity, which is a phenomena in electromagnetic waves. So we have the phase velocity is represented by Vp and the group velocity as a Vg. The phase velocity of a wave progressing with a constant phase, we consider that, and let us take an electromagnetic wave traveling in the positive z direction, which has the constant phase given by minus beta z plus omega t. So let's take that minus beta z plus omega t is equal to constant as equation number 1. Let's also differentiate this equation number 1 with respect to time. We take the here the beta being the constant, while the z is the direction along which the wave is propagating. So also we take the omega be the constant, that is the velocity, the angular frequency, the frequency of the waves to be taken one particular wave as a constant. So when we make the apply the differential, we get the dz by dt, arranging this plus minus sign as well, minus omega is equal to 0, or Vp is equal to Vp beta is equal to omega, or Vp is equal to omega by beta. Let's call this equation number 2. When a signal is conveyed or transported from one point to another, it is always necessary to modulate or mix by some other means, mix the signal to, in order to propagate by other means of a carrier frequency being transmitted. Now, after modulation, we have a group of frequencies centered around the carrier signal that must be transmitted along the guide. Now, if a phase velocity is a function of the frequency, different frequencies in a group will have different velocities. Now, because the frequencies are different, then they obviously they will have the different phase velocities. Now, the wave combine to form a modulation envelope, which is propagating as a wave having a group velocity. Now is defined as Vg, which is Vg is now is a function of the, because now frequencies are changing with respect to now the beta, which is a propagation constant now. So but it is now depending upon the beta. So d omega by d beta, we now take the differential of that, changing the dependence of omega on beta. So Vg is now the rate of change of the velocity, the angular frequency of those wave having the phase velocities with respect to the beta, that will be defined as a group velocity. Since we have the gamma square is equal to L square minus omega square epsilon mu, putting the value of gamma, which is now in the complex form, which we get the minus beta square. So putting that in this above equation, what we get, beta square is equal to omega square epsilon minus L square. Since L is equal to m pi over a, so beta square is equal to omega square epsilon mu minus m pi over a. Now differentiating this equation number 4 with respect to omega, what we get now, the 2 beta times d beta by d omega is equal to 2 omega epsilon mu minus 0, this term as used as a constant, or d beta by d omega times beta is equal to omega epsilon mu. Call this equation number, this one is 4, this one is 5. Since the phase velocity is omega by beta, and epsilon mu, the phase velocity is equal to inverse of the square of the phase velocity, or v square. So what we have, putting in equation number 5, what we get, beta is equal to 1 over Vg, which is the group velocity, is equal to omega epsilon mu, or Vg is equal to we have omega over beta. This is now the v is the velocity of the wave, combined wave. So what we have, omega over beta will be now the phase velocity, vp. So what we get, the v square is equal to vp times vg, where v is the speed of the wave with the combined velocities, the phase velocity and the group velocity. Now here this diagram will show that, this figure will show that the group velocity and the phase velocity, how they are linked. This is the envelope, okay, and it's carrying a particular frequency having the phase velocity, while the envelope has the group velocity traveling with the group velocity vg, while inside the envelope there is a multiple, we might have signals inside combined together, where the modulated signals are being mixed, and we will have these various phase velocities inside a particular the group of the waves traveling. So like the light we have got in 7 colors and multiple other wavelengths, other frequencies we have got over there, they travel in the form of group. So they have the combined group velocity, and this is the phase velocity of the internal individual, or the modulated signals, modulate the signals which are contained inside the envelope. They travel all along the z, moving towards the z. Let's watch a video, an emitted video, in which the phase velocity and group velocity phenomena has been discussed. That is a very nice video, will give you better understanding.
Suppose we add several waves together to create a new wave. If we change the amplitudes of the waves, the resultant wave also changes. The waves can have different wavelengths. The bottom wave has a slightly different wavelength than the other two. As we move the two other waves, notice how the sum of all the waves changes. The resultant pattern moves at a different speed than the original waves. We refer to the speed of each original wave as the phase velocity. We refer to the speed of the resultant pattern as the group velocity. When we have a wave describing a quantum particle, it's the group velocity that determines the velocity of the particle. Any wave function can be thought of as the sum of waves of many different wavelengths. For a quantum particle with mass, such as an electron, the waves with a shorter wavelength have a faster phase velocity. For classical water waves on the surface of an ocean, the waves with a shorter wavelength have a slower phase velocity. When different wavelengths have different phase velocities, we can have dispersion, where the waveform has a sharp peak at one moment in time, but is dispersed at another moment in time. On the other hand, if all the different wavelengths have the exact same phase velocity, then the pattern can stay constant, and the group velocity will be equal to the phase velocity. Examples of waves where all the different wavelengths have the same phase velocity are electromagnetic waves through a vacuum and waves on an ideal string. If we have waves with the same amplitude and speed, but moving in opposite directions, then we produce what we refer to as a standing wave. Much more information about waves is available in the video Waves, Light, Sound, and the Nature of Reality, and in the other videos on this channel. Please subscribe for notifications when new videos are ready.